lunch. And in the evening, we will have our ceremony and wrap-up meeting. So if possible, please keep staying here till the end of this workshop. So you can get the information at the website here. And you can get all information in Slack. So please register Slack. And if you don't, please do it as soon as possible. And the first keynote is given by Daisuke Iwai, Professor Daisuke Iwai from Osaka University about projection mapping technologies. So just after this opening ceremony. And the second keynote will be given by Professor Kim from Korea University, who was general chair of last APMR. And Professor Kim did great contribution to the standardization of AR/MR technologies. So I heard that he's going to talk about such kind of topics. And I and APMR 2022 gives thanks to the organizing committee members, program chairs Hideaki Uchiyama from NICE, and Shunrei Sai from National Chinese University from Taiwan. And as financial chair, Takafumi Taketomi from Cyber Agent, and publication and web chair, Yuichiro Fujimoto from NICE. And as local organization chair, Mariko Isogawa from Keio University. So please, thanks to the organizing committee members. And we have to give big thanks to ICAT and EGVE also, because we have joint meeting together, and the ICAT and the EGVE is offering us of venue and facilities, both on-site and online. And last night we could enjoy joint excursion and much more support from ICAT and EGVE. So please thanks to ICAT and EGVE here once again. So this is all for me. So after all, it's up to you. Please enjoy APMR.
Hi. Hi, good morning. My name is Hideaki Uchiyama. I'm a program chair of both ICAT-EGVE, and APMR. From my side, I'd like to introduce the detail of APMR this year. First, I'd like to introduce the participant. This year, we have the on-site event, and for, how can I say, 1/4 people will attend online, but 3/4 they are physically attending this year. And also, in terms of country, we got many participants from Japan, also Korea, and we have hopefully we can get the participants from Germany, Taiwan, and Australia. And about the submission categories, this year we prepared 2 different ones. The first one is a kind of a regular one. We prepared a long paper and a short paper. And for this paper, the paper will be published in the proceedings. And also, from the reviewer, you can get some kind of feedback to improve. There are some positive feedback. And also, we have the session called Pitch Your Work. Actually, in this session, you can sort of present any previously published work on the ongoing work rate, breaking result, on the anything you can introduce. And this will not be published, but actually for this session, hopefully this year we got so many excellent papers. Like some were presented in the top conference. So maybe in this session, you can see some, in many fields, we have some good, how can I say, papers, pitch your work presentation. So please also enjoy pitch your work presentations. And today the session is composed as follows. First, we have the keynote by Professor Daisuke Iwai. And next, we will have the first pitch works session. Then after the lunch, as Professor Kitahara announced, we will have some greeting at the first session. So at this moment, please come here on time, because we want to take a photo or something. Then after that, we will have the second keynote by Professor Gerard Kim. Then after that, we have the regular papers presentations. And finally, we have the another pitch your work second pitch your work presentation. And about the detail of the presentation, we are really sorry that, because fortunately we have so many papers this year, so we may need to limit the time. So for full paper, the detail is like this one. So please try to keep the time, because our schedule is really tight this year. And we are really sorry that for pitch your work, we are not able to have the QA time during the session. But actually, we have already prepared the Slack. So if you have any question or something, if you want to communicate with the authors of the pitch your work, please do that on Slack. So, and also on Slack, please try to write anything, any comments. It's really welcome. And actually, during the QA session, the session chair will pick up some questions for the time. So basically, the QA will be asked by the session chair. And also, after the presentation, something, for the presenters, please check the Slack, our Slack, and then please try to answer something. Okay, about the proceeding, actually, this year we are trying to publish online, and we found that some good one, which is called the CURWS. Actually, this is a kind of the archive for the proceedings, and this is, how can I say, maintained by Aachen University, so it seems good. And this was sort of supported by the Professor Fujimoto. He worked hard to actually, this is the first time to publish our paper here, so he worked so a lot. So after the session, please thank him. And also for the APMR attendees, actually we would like to have some best presentations about this year. So after all of the sessions, actually on Slack we will announce the URL for this. Then on Slack you will find the link, and please select 5 good you prefer the presentation. Then after that, we will try to find the best presentations awards. So for me, that's all. So please enjoy APMR 2020 this year. Thank you. Okay, so in 5 minutes, we will start the keynote. So actually, before starting, I would like to introduce something for this keynote. Actually, this is a joint keynote with ICAT and APMR. So for the ICAT attendees, please write a comment on the Discord. But for the APMR attendees, actually we are using the Slack. So for actually, I will check the both channel. But yeah, and also because after his presentation, he need to leave. So maybe it's better to ask if you have any question. It's better to ask right after his presentation or during the QA sessions. So it's almost time to start. So at first, I'd like to introduce the keynote speaker, Professor Daisuke Iwai from Osaka University. He is now associate professor at the Osaka University, and his research interest is projection mapping technologies, which will be talked today. So the title of this presentation is the projection mapping technologies for permutation of digital flexibility into the physical world. So please begin.
Thank you, Uchiyama-sensei. So thank you very much for coming to this keynote session in the very early morning, especially for Korean people, friends, because you are, I think, watched a soccer game last night and very enjoyed it. Yeah, congratulations. And yes, so thank you for the organizers of ICAT-EGVE as well as APMAR to give me such a great opportunity to give the talk about our projects. And I am very sorry because I couldn't attend ICAT-EGVE and will not be able to attend APMAR other than this session because of my family issue. But I hope to talk to many people here in this occasion. And I will stay here until before I have to leave before the closing session, but I would like to talk with you a lot after this session. So the title of this talk is Projection Mapping Technologies for Permeation of Digital Flexibility into the Physical World. So actually permeation, the word, this is my first time to use this word, so I'm also very unfamiliar with this word, but I like this. I found it in a dictionary, and I found it's very, probably it's a very nice word to express my research. So digital flexibility is, so nowadays you can, so my talk is more on visual sensation side, so no like haptics or sound, auditory or the other sensations, but I'm focusing on the visual sensations. So for visual sensations, the digital flexibility in computer graphics is, so you can write, you can draw, you can render any materials, any objects in a world. So you can reproduce anything in computer graphics, and you can. So actually, showing this picture, actually this is 100% computer graphics. You can do anything, I mean, from this. Or you can, like, so you can switch back and forth from a really low materiality rendering to the high, very rich material information in a computer graphics. So this flexibility is really great. So my vision, or I would like to, or our group would like to, how can I say? permeate. Digital flexibility permeates physical world. This is probably the vision of our research. So we want to control the appearance of the real world as we wish, like in computer graphics technologies. And we focus on projection mapping technologies to realize that kind of world, because as you might know, the projection mapping technologies are very good or nice tool to change the appearance or the texture or the material property of the real world real world objects around us. So, but at the moment, this technology was used probably only, not only, but almost the application field is entertainment and advertisement. But I think this technology has more potential, and we can use it for more different application fields. Maybe I will talk about more applications in the last of this talk if I have time. But yeah, I think this technology has a lot of potentials. And nowadays, the projection mapping is, we can project any object, images, any objects nowadays. Like, so the human face, trees, or architectures, buildings. Oops, sorry. Pointer. And buildings, furnitures, and human bodies, as well as this is, I don't know if you can see what is this, but this is in an aquarium, and these people project images onto a fish body. Maybe, I don't know if it's ethically okay or not, but everything, almost anything can be projected. But as you may think, so these surfaces are not suitable for projection. So this surface, the projection surface, white, uniformly white planar screen is very good for projection, but the other things are not suitable. And the projected image quality gets worse. So traditionally or conventionally, in I don't know, 20 or 30 years, researchers try to solve these problems. For example, the geometric correction. So if the surface is like this, so the 3D shape surface, then if you project image without any consideration, then you can get this kind of projected result, in which the projected image gets deformed. But if you apply a proper geometric correction technique, you can get this kind of result, like so as if you feel that the projected image is fit into the object. Or photometric correction. So if you want to display this image onto this type of textured surface, then you can get this image. Yeah, so the background surface becomes visible in the projected result. But if you if you compute each pixel color, considering the reflectance property of the surface, then you can get much better result like this. So this is photometric correction. Or the projector gets easily blurred if you project onto the 3D object. So like this is target image, and if you project this image onto a surface which is out of focus of the projector, then you can get this out of focus projection result. But if you apply a defocus correction technique, then you can get better result. But for example, other than that, there are different types of correction techniques. But these software-based, I would say, X correction technologies are limited. For example, this defocus correction. So this is target image appearance. So look, and this one looks better than original. How can I say? Without compensation, but still the image quality is not perfect. So I'd like to say. So the software-based technique is good, but still has limitations. And the one solution or one approach that can solve this limitation, I believe that it is computational displays technology or approach. So computational displays is defined as the technique that in which the joint design of display optics with computational algorithms and perceptual considerations defined in this article. So the key point is, from my point of view, this computational displays approach actually not only design software technologies or algorithms, but also display optics as well as and considering the human perceptual property. So, and actually this approach breaks the barrier of the display hardware limitations. And but particularly, specifically for projection mapping, actually we can also optimize in this whole system. That is, the surface, projection surface has also an essential component of the projection mapping technology or display. So we consider that, so we try to also design the projection surface to realize a better projected image quality. So this kind of end-to-end optimization framework is, so we are very interested in this kind of framework. So I'd like to introduce several, some part of our research projects which based on this concept. So first, I'd like to show you some result of the surface design or optimizing the surface for the projection displays. So, this is not good. Give me a second. Okay, this is much better. So, so this is, so in this research, we want to increase the contrast of the projected result. So if you project an image onto the surface, so this is image showing white paper, and on the white paper, we printed this pattern. So white is not printed, but the black box in a printed paper. And this is projected image, almost same appearance, but this is projected black. And as you can see, this is projected black, and this is printed black. And you can see, maybe you can see that the projected black is very black, and printed black is a little bit black. But so you may think that, okay, so projected black is already very good. But if you superimpose these two images, or overlay these two images, then we can find that the overlapped area becomes much darker than the other two areas. So this means that if we want to make if we want to realize or display a very high contrast image, then projected content and as well as the surface the reflectance pattern should be also optimized according to the projection image. So, sorry, this is, So this is one of the results of our research. So we project, maybe here. This church image is the target appearance, and we print out this church image on a sheet of paper and project an image onto this printed paper. So the top left image shows this or superimposing result, and on the top right image is projecting this texture onto a white screen. This is just a projection image, and this is a printed church image under uniform illumination. So, and we capture it using different exposure time. Then you can see that this projection only and printed only appearance becomes washed out very quickly, but still we can see still some details in the dark area in our method. So this shows that we can realize a very high contrast result. And maybe this is one of the application. So still my age, in my home, there are some pictures, printed pictures, not on iPad. And these printed pictures can be more highly realistic by projecting some patterns onto it, like this. So that was only 2D, but nowadays we have a 3D printer which can print out full color textures. So we can use this printer as a projection target to realize a high dynamic range or high contrast projection mapping result like this. So on the left, we print out a texture object and we project the same texture, not same, but almost same texture onto that object. So this gives us a much higher contrast than the printed object only. And that was only, how can I say, static, right? So the printed, once we print object, then the texture is not moving. But so in the next project, we try to dynamically change the reflectance pattern on a surface by using photochromic material. So photochromic material is, the name of this material sounds like very, how can I say, unfamiliar, but actually I think you sometimes use this material because this is used for UV checker. So if you have a UV, this tool, you go outside, then the UV checker changes its color, and you go out inside, then this UV checker also changes the color. So to see how much the UV light is illuminated onto your body. And this material, so by using this material, we think, okay, we can change the reflectance pattern or spatial reflectance pattern on a surface. So, and we built this kind of small setup, so this sheet of screen is painted. We paint the photochromic material onto this surface, and behind this surface, we placed this UV LED array to change the reflectance pattern spatially varying manner. And so this is one of the results of the reflectance pattern modulation. And yes, we project this dock image onto the surface. Then this is the target image. And this is the projected result without the reflectance modulation. Then if you compare this eyeball area, the blue means more dark and red means bright, and this blue, eyeball area becomes a little bit still higher in this result because of the interreflection of the light. But if we apply our method, our method changes the reflectance pattern, then we can get much high contrast image in this result. So other than that, for example, if we use the surface design, if we design surfaces not only for high dynamic range, but so for geometric correction as well. For example, in this research, we use infrared marker as a marker of infrared ink for marker of the, how can I say, tracking the object shape or deformation like this. So so if you paint some texture onto the object, but which is very deformable object, but once you paint, then if you deform it, then the texture is not deforming if you don't track it. So in this research, we use infrared ink, which is very visible in an infrared camera image, but it's very little. I mean, it's very slight intensity difference in human eyes. I mean, in the visible spectrum. So we use this pen for the marker for tracking the deformation of the deformable object. So this is, yes, so yeah. So in an infrared region, we can see the marker, the pen textures are very, very visible. And we track this deformation by using the marker tracking. So according to the marker movement, we change the projected texture. Yeah. So that was a more passive style, but we also do more active marker embedding. We embed some IR light inside of the IR light sources inside of the projected object. So, and we actively modulate the IR pattern, IR light pattern like this. But we didn't embed IR LED inside of the object, but we actually embed the optical fiber, and we place IR LED on the bottom of the object, and the IR light from the IR LEDs guided through the optical fiber to the object surface, the surface of the object. And this optical fiber can be printed out from a multi-material printer, a 3D printer. Oh, okay. So this is the object, and on the bottom of the object, we make a holes for putting the IR LEDs on the bottom. Because this is IR light, we cannot see it in our eyes, but of course the computer vision technologies can track this marker. Okay, so the surface design is over, and the next topic is display optics design. So the first one is extended depth of field projector by fast focal sweep projection. So we place liquid lens in front of a projector. So this liquid lens can change the focal length very quickly. Like this is now it's 5 Hertz. Then we can modulate the focal length of this lens at 60 Hertz. And if it's 60 Hertz, when it's 60 Hertz, we cannot see the modulation because it's higher than our critical fusion frequency. And by using this device, we can actually move the focusing point back and forth very, very fast, such that we cannot perceive this modulation. So like this. And actually this modulated focusing pattern becomes consistent between this modulation range. And we use this phenomena to extend the field of view, depth of field of the projector. Maybe this is intuitively understandable. So for moving object, this is the projected result of our method. So as you can see, the details are always, how can I say, the image gets focused always, but this is normal projection. So as you can see, at some point, the image gets blurred like this. Wait, it's very fast. So this is our method, focal sweep projection. So the details are still there. I mean, we can see some details in the projected result every time, all the time, but for the normal projection, sometimes the image gets blurred. And So that was in that research we place this focal tunable lens in front of the projector. But for this research, we use that lens as our eyeglasses for 3D stereo display to solve the divergence accommodation conflict. So in a normal 3D projection mapping technology, like so in this case, so the liquid crystal shutter is used to give different appearance of the projected image for each eye to give a stereoscopic view like this. But of course, there is a divergence accommodation conflict because human eyes focus on the surface, but the displayed object, the depth of the display object here. So this discrepancy is not good for our perception. So we place this ETL, focus tunable, electrically focused tunable lens in front of our eyes, and then we can change the focusing point of the view by modulating this lens very quickly. So, in doing this, so we project so the synchronized projector projects this object, this image, synchronously to the ETLs and LC shutter. Then we can get stereoscopic image projection without having the divergence accommodation conflict. Maybe this one. Sorry. Okay. So we place real objects at 3 positions, and we project 3 bunny image onto the flat surface, which has the same depth from the camera. And actually, the top bunny goes to the very far, and the middle bunny is at here, and the bottom bunny comes to very near, like around here, by our method. And this is the captured image. So from okay. The focus point of this camera changes from far to near. And now it's far, so these 2 images get focused, and now the focus point becomes here, and these 2 objects are focused, and finally these 2 objects get focused. So from this image video, we can see that these 3 objects, bunnies, are projected onto the same depths, but that these objects can be focused at different depths. And by using this technology, so this is the real setup. So human actually wears this focus tunable lens as well as the LC shutter. So when you look through this system, you can see the bunny like this, and we check the how can I say, the perceived distance using this device. Then we find that using our method, the perceived distance becomes much correct. I mean, more accurate than normal 3D stereoscopic projection display. So, yeah, the error becomes very small. Okay, so the next topic is again so different than the focal length stuff, but this one again geometric correction. So maybe some of you knows this technology, light pen, which is the great invention by Ivan Sutherland, like a very early stage of the touch pen. So the light pen, this is the principle of light pen. So this is a CRT monitor, And CRT monitor actually draws an image by a scan line. So the light scan from top left to bottom right like this. And so a point on the display panel becomes bright once in a frame at a very specific time. So if you measure this timing, then you can know the position of this display panel, this pixel in the display panel. So this phase information, temporal phase information, actually is identical to the spatial position on a display. So the light pen is the technology that can sense this position by using a photodiode. There is a photodiode inside of the pen to know the display panel position. So, and actually, I don't know how many years ago, but maybe 20 or 30 years ago, the Nintendo sold this kind of gadget, and this is also uses the same principle. So the CRT monitor, so this watches the CRT monitor, and the bright timing is used to know where the gun aims at inside of the TV. So we use this technology in this principle in projection mapping. So like this, so we can display, or we can project some images, fit the image onto the bunny, even if the object moves or the projector moves. And this was done without using the camera, because we use this light pen technology. So, okay, so actually we are using this laser scanning projector, and laser scanning projector actually scans a laser beam from top left to bottom right like this. So, and we place a photosensor on a projector surface, then we can know the position of this photosensor from the time information. So this is drawing application like this, and when we embed this photosensor in our scene, then we can do this kind of applications. Yeah, and stitching. And we also use this technology for drone projection stuff. We place a laser projector on the drone, and we can, how can I say, display some images onto a wall on which the photosensor is embedded. Okay, so the last topic is perceptual hacking. So the cross-modal, we are interested in the cross-modal, how can I say, phenomena. Probably the Anatol, the keynote speaker, also mentioned about it. I'm not sure, but maybe he is the inventor of this cross-modal stuff. And the cross-modal perception is perception that involves interactions between two or more different sensory modalities in a brain. So for example, if you touch a surface and if you feel it's smooth, but maybe if the texture of our hand becomes like this, then probably the brain was hacked by this projection image. Then we feel that, okay, maybe the surface becomes rough. I'm not sure, but maybe, I don't know. Or if we change the texture of our hand, then like this, then we may feel that the surface becomes bumpy. We are not sure, so we try to we investigated how we perceive, or how our haptic sensation is modulated by the projection image. So first we checked our thermal sensation. So if we change the object color or if we change the hand color, how these color information change or modulate our thermal sensation. And actually it slightly change our thermal sensation. Like if we change the object color like blue, then we judge this object warmer than a natural color object, for example. Or if we change the hand color, then this effect is inversed. Like, so if we change our hand color blue, our hand becomes blue, then the touched object is judged as colder. So this is, yeah. So this is one result. And so we also change, for example, this is that was color, and the next one is the shape. So when we touch this object like this, but if we deform this object, visually deform this object, and while touching, then maybe we feel that object shape is changed. And this is one of the projected experimental result. So physical shape is like this. And we modulate the shape like this. So the virtual shape is like this. Then how we feel, we investigate how we feel the surface shape of the object. Then we found that surface shape becomes slightly modulated. I mean, perceptual, how can I say, haptically perceived shape becomes a little bit biased up towards the visual information. And another example is softness perception. So when we push a soft object and the textures gathers towards the pushing position, right? So we actually enhance this movement by projection mapping. Then we found that this visual effect actually changes our softness perception. Like if we move the texture more, then we feel that the object becomes softer than the actual softness. And we also changed the actually fingernail color. Like if we push, then we change the fingernail color red, then we feel that object becomes more softer, actually. So, yeah. So recap, so the computational displays approach for projection mapping. So we did some projects on this topic, and yeah, the point is not only the display optics, but also the surface, projection surface is one of the projection mapping components. So we also consider, I mean, we think the optimization of the projection surface is also very essential in the projection mapping technologies. So, but until now, I'm talking about different technologies for realizing or for increasing the projected image quality. But I was always thinking that, but is it really natural or not? I mean, I think it's, if you see the projection mapping in a movie or in a photo, it's really great, or it looks like very cool, or it's very beautiful. Or if you see it in the real world, still you think, okay, it's very nice. But I think it's, I'm not satisfied with it because it's totally unnatural. For example, the projection mapping only works in a dark environment. For example, in these rooms as well, right? So here, my position, I'm in a dark area, I'm in a dark. Because if we turn on the light, then the projection, how can I say, this presentation image gets completely washed out. So projection mapping works only in a dark environment. I think this is really, really hard limitation in projection mapping. Or shadow. So this shadow is also very much a problematic problem. So these two factors actually make the projection mapping really unnatural. To my, this is my opinion. So I would like to So we are now actually, so currently we are trying to solve these problems. And I would like to introduce some very early stage research results. So first one is shadow. And shadowless projector. We tried to realize a shadowless projector, and we inspired by this surgical lamp to realize a shadowless projection mapping. So surgical lamp actually is a very interesting equipment. It's very simple, but it solves the shadow problem very in a wise way. So if the light, so when this light is blocked by the hand of the surgeon, then this light does not reach to the area, which is very important area. But actually, other LED lamps actually also turns on. So these lamps actually illuminate this important area. That's why there is no shadow, hard shadow in a surgical lamp. So inspired by this phenomena, we built up this system. So this ASCA 3D optical element is actually originally used for floating image display, but we use it for projection mapping. And we place a dummy proxy object on top of this scene, and this is target object, and these two objects are like placed at the plane symmetrical position. And this optical element actually works like this. So if there is a light source, then the light, how can I say, diffusely, how can I say, sorry, I don't know how to express in English, but the light goes like this, right? And this light actually gathers onto the corresponding point on the target. And so by using this phenomena or principle, optical principle, we realize shadowless projection mapping like this. So on the left, this is normal projection mapping, so where you can see a lot of hard shadows, which is not good, but it's normal. But on the right, this is our shadowless projection mapping result. And you can see that even if you cover the object very, very a lot, but still we can see some textures onto the bunny. So I think this is one of solution for the shadowless, for the shadow problem. But I would like to say this has a lot of limitations. For example, if you have to have a large space for this target object, so you need a big box, over the projection target. So this is one of the limitations. Or this target object cannot be moved at this moment. But maybe this is this is the first attempt, and we would like to improve this situation by applying different technologies. We are thinking about it now. Okay, so let's move on to the dark environment issue. So dark environment is, of course, it's very much limited. It's not a good thing, but also actually this environment light is also very important key for our material perception. For example, if you see this image, then maybe you perceive that, okay, so this image is blurred from this image. Yeah? But if we synthesize this image, this is actually a copy. The center, this sphere is copied from this image, just a blurred image of this, the center image, and this area, surrounding area, is copied from the center of this image. Then you perceive that the material of this center sphere is completely different from this sphere from the middle image. So this perceptual difference comes from the environment information, I guess. So this example shows that is the evidence of that of the environment light is quite important for our human perception to see, to understand the object in front of us, even in a projection mapping, I believe. So, but if we, so as I already told you that the environment light breaks the illusion. So if we, so this is very good projection mapping result. It's the details of the projected result is quite clear. But if we, once we turn on the environment light, then everything is gone. So I would like to solve this problem. So one solution would be to replace the environment light by projectors. So we turn off all the environment light, and we place a lot of projectors on the ceiling, and we use the projectors as the environment light. Because the projectors can spatially control where we want to illuminate or where we don't want to illuminate, but we want to do the projection mapping. So, so this is also one of the first prototype of this concept. And we use 7 projectors. And if we, so this is normal projection mapping in a dark room. So this is, of course, this is very good. But once we turn on the light like this, so the projected texture becomes very, very bad. But if we replace, we turn off the environment light and we reproduce the environment light by projectors, then we can get like this kind of image. So it's much better than this one. So this is also a very, very fast prototype, and we would like to improve a lot. We need to improve a lot, but I think this is one of the one direction to solve the environment, I mean dark environment problem. And also we can realize this, specular. We can how can I say? We can realize specular reproduction, specular object reproduction in a projection mapping at the first time in this system. And so that concept, actually this concept is not only for the material reproduction, but I think, or the dark environment problem, solution for the dark environment problem, but also we can use this, how can I say, replacing the environment light with the projectors can be also used for other applications. So for example, if we, so this is, we use the electrically focused tunable lens as our eyeglasses, and using a projector as an environment light, then we can actually modulate the spatial resolution, or how can I say, spatial frequency of the real world by combining these two technologies. And yeah, so this is focused tunable lens, and we use these lenses as eyeglasses. And yeah, this is a simple principle. Oh, sorry, this is, so. Yeah, so when ETL, the focusing position modulates like this, and we use high-speed projector to illuminate, I mean, this is a synchronized high-speed projector as the illumination of the scene, and we illuminate the scene like this. So, wait. Okay. First, oops, sorry. Okay, so first, when the focus, this pin is focused, then we illuminate these two objects. Then, when this apple is focused, then this apple is illuminated. And we do this very, very quickly, I mean, very fast, like more than 60 hertz. Then actually human will perceive this. the center ball, the soccer ball is blurred, and the pin and apple becomes clear. So this is not possible in a natural world, in our because this is not optically natural, because the only the center object gets blurred and the far and near objects get focused at the same time. This is not possible in a real world, but this can be possible in this framework. And like this kind of this technology can be used for the navigation, maybe. Like if instructor wants a trainee to focus on this part, then or you can use this for your instrument training. So the focusing area is follow the score in a good tempo, for example. Or if you when you study, if you wear this system, then you cannot see the object other than the textbook. So you have to focus on your study. So if there is a comic book around the textbook, you cannot read because it's totally blurred. Okay, so maybe I think this is time, right? So there are several applications, but I think it's better to have a question at this moment. Sorry. Yeah. Thank you.
Thank you, Yoi Sensei. It's so impressive presentation. Okay, now it's time for the question. So actually, I have one question. Actually, for me, Yoi Sensei's work is always, how can I say, you select the how can I say, good hardware. Actually, hardware design is so unique for me. So I'd like to ask you, how can you come up with the sort of hardware design? For example, ink, lens, and also I forgot, for the shadowless projector, you use some special plate or something. How can you come up with such kind of idea?
Thank you very much for the question. I don't know. Maybe, but I always thinking about projection mapping, the limitation of the technical limitation of projectors. And I want to solve. There is a list of the limitations that I want to solve, and I sometimes go to like industry exhibition, and I found this object, this system is very interesting, and sometimes maybe this can be used for this problem, maybe.
Like so, you visit some exhibition to get the idea or something.
Or like email.
Okay, thank you. Okay, do we have any question from the audience?
Thank you for the exciting presentation. I have two questions. One, in the example of where you replace the ambient light with a bunch of projectors,
Yes.
are you actually basically like reducing the ambient light toward the target object, and for the rest of the environment, you'll maintain the rest of the environment brighter? Is that basically how this is done?
Yes, that's right. Yes.
And
So
my second question is, you showed a lot of examples of like embedding some kind of a marker or LED on the object
Yes.
for the purpose of tracking it.
yes.
Is there any reason you took this approach instead of using like depth sensors and SLAM and all that? Is there a particular reason for that?
Yes. For the first question, that's true. So actually, if we turn off the texture onto this object, and then this object becomes very, very black. So this means that all these illumination is done by projector. Yes. And the second question, regarding the second question, why we use this kind of infrared marker other than using, other than the SLAM or the other technologies, because I think there are some research using this kind of the SLAM or other markerless technology to realize the projection mapping. But I think, especially when we use multiple projectors, then the overlapping area. So for multi-projection mapping, I think the most difficult part is this geometric correction, because even if a slight misalignment occurs, then we immediately perceive there is an overlap or a seam between two projectors. So the geometric alignment should be really, really accurately done. So that's why I use the marker-based technology.
Thank you.
Thank you, Iwai Sensei. I have a question about the spatial blurring that you presented at the end. So, do you know if you can affect people's perception of depth by it? Since the blur of an object is also a depth cue.
Yes, yes. I think that's a very good point. This in a 2D, in 2D image, the captured image, this looks like great. But if you wear the eyeglasses on your eyes, it's a little bit strange feeling, because when we want to focus on the blurred area, we cannot focus there. So it's very, very unnatural. Yes. So I think we have to consider the application very carefully, because otherwise we will feel sick, for example, by this.
The other depth cues are conflicting, maybe.
Yeah.
Yeah. Okay, I see.
Actually, the order of the research is this is first, and we think, okay, this is unnatural. Then we go to this multifocal. Then we do this research, you use this technology for more realistic, for more natural representation. Yes.
Very interesting. Thank you.
Do we have any questions?
Thank you, It's a great talk. And I'm curious about the IR marker for the deformable object. In that case, do you track the marker in 2D space, or do you estimate the 3D deformation?
This 2D, only 2D, because we use we use this coaxial projector camera system. So we don't need the 3D information for this research to align the projected image onto the object. Yes.
Okay, thank you. And I have one more question. It's okay. And I also curious about the multi-projection mapping system. And do you have any knowledge how to arrange the multiple projectors to cover the this kind of room?
You mean the placement of the object projector? I think it's more manual. There is no automatic method to how can I say, determine the optimal position of the projectors. But I think, oh no, maybe there is. There was a research. They optimized the position of the projectors, but yeah, I think it's not a big research topic at the moment. Yes.
Okay. We have any question? Actually, we got one question from the Rob Lindemann on
Hi.
Discord. I will read it. Thank you for the excellent talk. What do you think about the projection mapping for the diminished reality? Can you adjust the color to remove object?
Thank you, Rob. Very good question for my rest. So in the application, so I didn't talk about application, but one of the application is that, so this is very old actually. So this was my PhD research. Sorry. So we diminish the book actually to see through the, how can I say, pile of the books from the top to the bottom to make the book search easily. Yeah. So this actually changes the to diminish the how can I say, the existence of the real object by using projection mapping technology. Yes.
Thank you. Do you have any questions, comments? Okay. So if not, actually, it's almost time. So let's, Iwai Sensei, thank you for the excellent talk. Let's thank the speaker again.
Thank you.
Actually, after this talk, actually, the APMR have the oral session here, and the ICAT will have the posters here upstairs.
our last poster interview for today, which is proposal for motor skill training considering spatial awareness and cooperative action involving third hand. And we have the authors to quickly go through with his work for maybe 45 seconds to 1 minute. Okay, so for this research, we're actually focusing on the training for three-hand body in VR. We want to see that if human can actually get use of this kind of unnatural shape of the body, and then if they actually able to feeling comfortable about it, then what change in their behavior that leads to this kind of improvement? So we designed a training task in VR for 30 minutes, which compose of both touching task for training the spatial awareness around the three-hand body, and a drum the fire task, which which is training for the cooperative action of the three-hand body, which as shown in the video like this, so that they will touch the user will touch the fires in order to prevent them from shrinking. Yeah. And before and after the training, we have the evaluation of a bottle dragging test to see that whether they actually improve in their general performance. So for now, the result actually shows quite a positive improvement after the training, which did indicate that we have successfully conduct the skill transfer for the three-hand body and then makes them feeling more comfortable. And there's also some kind of change in their behavior. For example, like the left hand works more in shorter distance and third hand works more centrally. Yeah. So for the future, we actually want to see that if there's any change in their body perception after this kind of three-hand body training. Yeah, that's all for it. Thank you. Thank you very much for the clear and crystal clear explanations. And because of the time, we don't really have any time for the questions. So just make sure that dropping any questions in the Discord or Zoom or even YouTube if you have any, and we will make sure to try to reach the authors for you to answer the questions. So thank you again. And now we will move on to the next demonstrations presentations.
Hello, I'm Kyoshiyama. I studied about investigating perception of multiple virtual hands using a state response. And I use nine hands to, and the procedure is EMG calibration and 2 minutes reaching task about red sphere and white sphere. And after the task, I gave stimuli and answer the questionnaires. And I there are a great many research questions regarding the use of multiple hands. Thank you, please. Please, yes.
Hi. Hello, everyone. I'm Ayumi Ichiko from University of Tsukuba. And here is our research investigating the effect of animal avatars on users' self-disclosure during interaction in various steps. We propose a one-on-one communication in which the user and the interactor use animal avatars in the VR space to promote users' disclosure. Self-disclosure mean process. People reveal, and oneself to the other. In this system, two users communicate and in a real space with voice call function. And during communication, users' movements are converted to animal That's all. This is an operation system to easily control the movement of the mid-ECG character. Um, we propose an integrated operation system that combines puppet motion capture and human body movements. Like this, arm movements of the character is controlled via the puppet's arm, and neck movements of the character is synchronized with the operator's own neck, like this. And you can move the special movements of the character. If the you can move the puppet back and forth. The mid the city character and also move back and forth like this. Of course, you can also move left and right and jump. Uh, the point is, the point is that the system enables to easily control spatial movement and multiple parts of a character simultaneously so that you can represent attractive movements of a character. Thank you.
So, uh, so the we developed a 20 component olfactory display. So 20 component olfactory display is the device that olfactory display can reproduce various odors by blending 20 odor components using olfactory odor components. So odor component were determined by analyzing mass spectrum data using non-negative matrix factorization method. In the device, 20 by mixing 20そうですね。Factory display is used by sending command from a PC simply. That's all.
the feature of our work is that so you can remap your body system between your movement and virtual movement immediately in real system. So as the previous research of human augmentation, I can come up with a third arm or sixth finger. So in those research, you can attach extra arm on your body. But so the problem is those research is that operating system is made by researcher, and it cannot be edited quickly. However, in our work, you can edit your body system just by changing the circuit in real system. So for example, if you misconnect the connection circuit, you move right leg physically, and virtually your robot avatar left arm. So in this way, you can design your input and output rapidly. And also, we developed some feedback system to increase the sense of ownership. Okay, that's all. Okay, this research is about the telepresence robot, which can convey the nonverbal information like gaze or pointing. But when using the physical robot, it needs some cost to develop or maintenance. So our proposal method is to replace the physical some body parts to AR. So どうしよう。ちょっとこうね。ライフスタイルをちょっと上げて、でもどう見せるどうしましょう。まあ、イメージだけ。Now we can't show you, but we replace arm to AR. Yeah. This.
So we made the centered virtual environment, and like it utilized the our olfactory display, which is the machine to scent emission, and the olfactory display uses this had the advantage like the of the precise temporal control of the intensity of the odor and also the mixture ratio, and also we beside this research we did the research about the combination of scents. So we utilized the research study into this virtual environment by mixing the two different smells. And also, in order to make in order to utilize the olfactory display's advantage of temporal control of precise, um, we use the scent emission in the landscape so that like the user feel the intensity more and more when they approach the odor source. So at the same time, we combine the information of the angle of the face in the landscape in the virtual environment tracked by the head-mount display here, and so the participant will experience the distance and also the angle-based intuitive olfactory experience. Yes. Thank you. That's all.
カメラ映ってるかな。大丈夫そうかな。So this is the over poster and demo presentation in ICAT-EGVE. So all of the demo and presentations are very scientific and great. So thank you for listening. よいしょ。
Hi, Rob. Can you start your sharing of promotion of VRST 2023?
I'm happy to. So can I share my screen?
Yes.
Konnichiwa. Hello, everybody. Going to share my desktop and see what happens with sound, video. Good. Yeah, sure. So is that coming through okay?
Yes, yes, we can see your screen. Thank you, Rob. Yeah, we can see your screen, Rob. Sorry, we can't talk both of us at the same time, so I'll close the microphone.
Okay, so you can hear me okay? That's
Yes, yes, no worries.
okay, good. So hello, everybody. I'm Rob Lindemann, and I'm thankful to the organizers for allowing me to give you a little teaser about the next ACM VRST conference, which is going to be held in Christchurch in New Zealand. And the tentative dates are the 9th through 11th of October of 2023. So in case you don't know, New Zealand is pretty far down in the world, and Christchurch is on the South Island of New Zealand, right in the middle of the South Island. The country itself, we only have 5 million people, and 1.7 million of those are in Auckland. Christchurch, where we're going to be, has about 400,000 people. And there's about 30 million sheep in the city, in the country, and about 12 million cows. So we're severely outnumbered by the livestock. And the other important things to remember is that there are lots of hobbits in New Zealand and only a few orcs. So it's a pretty safe place. So why Christchurch? So it's as I mentioned, it's the largest city on the South Island. It has a really good international airport with connections to one-hop connections to major cities and then two-hop connections to the wider world. The airport's very close to the city center. It's only about 15 minutes. There's lots of accommodation options, 3 to 5 star hotels, Airbnbs, even youth hostels and what we call backpackers. So there's lots of accommodation types. And then I think really importantly, ISMAR is going to be the week after VRST, as is SUI. So SUI and ISMAR are going to be co-located in Sydney. And Sydney in Australia is only about 3 hours from Christchurch by plane. So if you need motivation to come down, you can do all 3 of these events within less than a 2-week period. So it gives you a good opportunity to not only see these beautiful parts of the world, but also to reconnect with a lot of your colleagues and present your work in 3 very good established conferences. And why else? Well, because it's in New Zealand. And so here's some teaser pictures that I took. This is Mount Cook Aoraki, the tallest mountain in New Zealand. This is just out the backside of Christchurch. So there's lots of nature within about 15 minutes of the city. And this is a picture I took when I was out geocaching. Some of you know that I go geocaching. So this is a just beautiful, beautiful forest area. And as you know, there are some other creatures in New Zealand. So it's really famous for Lord of the Rings. And Weta Workshops has their artifacts all over the country that you can see. And Christchurch itself is a really revitalized city. So I know many of you know that there were some earthquakes about 12 years ago. And the city has really grown to be a beautiful, beautiful city after the earthquakes. It's also home to the HIT Lab. and we're just celebrating our 20th anniversary. And we have a huge number of pieces of equipment, some specialized equipment. At the top here, you can see what's called a Nova ball. This is a 360 ball that you can sit inside, and it's untethered and it rotates 360 degrees in all directions. And that's actually Tom Furness sitting inside giving it a go. And the bottom one is our multi-sensory VR setup, where we have sight and sound and floor vibration and wind feedback and smell feedback. And all of that is projection based, so you don't have to wear things. And so these are some of the things that you'll get to see. And we already have an organizing committee. And so myself and Hemi Fanga, who's a researcher at Massey University, are going to be the general chairs. And we put together a pretty strong and experienced program committee. And if you're interested in helping out, you can see that there's some posts that are TBD at the bottom. And so if you're interested in helping out, please reach out to me and get involved. That would be great. And as the nice thing about VRST is it's typically single track. So there's papers and panels and posters and demos and keynotes, and you get to see everything, which is really nice. I just came from VRST and Scuba, and it's a really nice thing to be able to see everything. So that's one thing. Here's just a map showing the connections. It might be a little hard to see, and I'll just skip that for time. The central city, Tepai, is the convention center, and it's right in the middle of the city, and it's surrounded by just beautiful places to eat and drink and to meet. The art gallery is really close by, and then there's a huge park that's all green space, very close. And this is what Tepai looks like from the outside. Is just completed last year. It's a beautiful, beautiful facility. And then New Zealand itself, there's just so much stuff to do outside. And everything from crazy sports that Kiwis do to really relaxing times and shops and things. So I'll skip these a bit. There's also really nice hot tubs, hot springs about an hour and a half north, which a lot of people go to. And so I'm going to play a short video. Hopefully this will play, and you can see this.
Kia ora. Find your space in Ōtautahi, Christchurch. In New Zealand's second largest city, you'll find space for every business event. Open air and wide open spaces, room to think and room to be free. Just 20 minutes from the international airport, you'll find a remarkable range of world-class venues and facilities. Choose from classic heritage to cutting-edge modern, intimate to immense. There are more than 2,500 CBD hotel rooms to select from, countless bars, cafes and restaurants to enjoy, all just moments away from each other, on foot or on two wheels. Find a space where you can go from brainstorming to boating, conference to culture, boardroom to blue skies, and trade show to trailblazing. Find a place that meets the changing needs of business events. Find your space. Find Ōtautahi, Christchurch.
Okay, so just in closing, everybody should learn a little bit of Te Reo Māori, so the Māori language. So you heard in that video, kia ora is what everybody says when you meet somebody. So you can all try that in the room. Kia ora. And I'll listen. Oh, I can't really hear. Okay, try it one more time. Kia ora. And I'll just assume that you did it. So again, it is pretty far. So in order to help entice you to come, so we're really coordinating closely with ISMAR and SUI so that the submission deadlines and that the conference dates line up very well to maximize submissions, and so everybody can come down. It is far, so bring your family, stay as long as you like. And this URL at the bottom, if you want to take a picture of it and look at it later, this is a 360 video that I shot in a lot of really beautiful, relaxing places throughout not just Christchurch, but all of New Zealand, in the forest and by the ocean and so on. And so if you look at this in a VR headset, because we are VR researchers, then you'll get a nice kind of feeling for what it's like in New Zealand. And so, yeah, I hope that you can start preparing your submissions and join us in Middle Earth for ACM VRST in October 2023. Kia ora. Thank you.
Thank you, Rob. I don't know if you heard the applause round, and people actually tried to say kia ora. So thank you very much. Okay, so we'll go on with the ICAT closing session now. Thank you again, Rob. Ivek, maybe we can go and... I guess. Mm-hmm. Nope. Yeah, I think you maybe have to switch your... Thank you. So before letting you go, we have a few more words to say. So ICAT-EGVE 2022 is almost finished, but we really hope you enjoyed it. And as you saw, we give you, we hope you will be back with us next year in Dublin, in Ireland. And so before saying goodbye, we have a few statistics and words about the submissions, and then we'll have the award ceremony. So regarding the paper submission, we received this year 39 really good full paper submissions, and the review process worked as follows. So we assigned 2 reviewers to each paper from the International Program Committee. Then we had a small quality check between the 2 of us, Hideaki and myself. And then when there was some kind of disagreement between the reviewers, we assigned a 3rd reviewer to get a better idea about what we should do with the papers. So what does it mean when the reviewer disagreed? It's actually when the difference in scores was higher than 3 in the review scale that's used in ICAT-EGVE, or when one score was a bit low, so we also assigned an extra reviewer to make sure everything was okay. And then we took the decision based on the average of the reviews. So in the end, we had, out of the 39 full submissions, 17 papers accepted. And so it was 16 long papers and 1 short. So that's an acceptance rate about 43%. And before saying the same about the posters and demo, I would really like to give a big thank to the International Program Committee, because as you realize, probably the deadline was extended multiple times for ICAT-EGVE this year. And so they had a shorter amount of time to do their reviews. So I put all the names here so that we could give them a big round of applause and thank them very much for their work for the community. So just a big of applause, please. Thank you very much, and thank them. So regarding the posters and demo submissions and statistics, there were 17 poster submissions. Actually, 7 of them were papers that were from the paper track that we proposed to resubmit to the poster track, and 10 direct poster submissions. So the review process worked more or less like the papers. There were 2 reviewers from another international and domestic program committee to review the posters. And as for the papers, when there was a disagreement or when needed, a 3rd reviewer was assigned. And again, the decision was based on the average score of the reviewers. So in the end, there were 15 posters accepted. And regarding the demos, there were 14 demo submissions, and in the end, 13 were accepted, and 1 was invited from IVRC. And now is the time for the award ceremony of ICAT-EGVE this year. And for this, maybe I'll give the microphone to Hideo Sensei, if you like. Thank you very much.
Okay. Hi, my name is Hideo Saito. Actually, I'm the Honorable General Chair, but most of the thing is done by actual General Chair, Maki Sugimoto. Thank you very much for organizing. But by the way, I'm standing here for introducing awards. So, first of all, next slide is okay? Yeah, okay. Yeah, here. Yeah. This one is a poster demo awards. So this is a way to selecting the poster demo. But actually, can I explain it, or somebody else is actually? Yeah, I think I'd like to hand the microphone.
Thank you. So this year is really a competitive selection for us because we have to try to find and try to pick the one that is best for us. And actually, we somehow get into the final process of struggling between one or two or three from each of the track, and we somehow made through it. And as you can see, we have a bit of the procedure to follow in the way how we decide the reviewing process, such as we have to do some of the formal selections, and then we have to interview each of the people. For those who might have already seen us during the interview phase, I hope that you really enjoy that. And yes, so to not further ado with that, I will go to the most interesting sessions for today. So please read out your attention. And we have lyrics into Cityscape, a mixed reality system for appreciating lyrics projected onto the cityscape while walking. And we have Rin Izumi, Shuhei Kodama, and Tokiichiro Takahashi. And could you come to the stage for the awards if you are here? Nope. So maybe we will keep that for you and make sure that you come here if you sing this. So next, we will move on to the Best Demo Award, and let's do it again. And we have prototype to control the mid-air CG character using motion capture data of a plush toys, and that's for Miyu Fukuoka, Shohei Ando, and Naoya Koizumi. And if you are on here, please come to the stage. Yep, we have the people. All right, so now we have for the paper awards. So,
Okay, next, I'd like to show the paper awards. And let me introduce those award committee members. One is Dennis Karkofe from TU Graz and Flinders University. And one more award committee member is Daisuke Iwai, who has already gone from here, but he made a good presentation, nice presentation this morning. So I asked them to select the award. But first of all, let me explain the award selection procedure. And all the paper is actually be reviewed, double blind, without knowing the authors, and the reviewers are also blind to give us scores. Then actually the program committees selected 5 papers based on the score of the review. So at that time, as I said right now, all the review score is given by the double blind, and almost automatically the program committee members selected top 5 papers. Then the 5 papers are also reviewed again by 2 award committees, Dennis and Daisuke, and they selected those award papers. So the review candidates is also they gave 7 scale points, then sort the candidates by the total score, and then they selected top 3 papers. Then finally, they choose 1 best paper and 2 honorable mentions. So that is a procedure. So actually, I was I need to be a member of the award committee member, but unfortunately, one of the 5 candidates seems to be authored by my colleague. I'm not so co-authored, but that's why I didn't do anything about our selection. But those 2 award committee members, there is no conflict with interest. So that's why I asked them. Okay, let me show you the award. Next slide is showing the award. Okay, so next one is the honorable mention. So please wait. Okay. Yeah. Okay, so first one is the honorable mention. Next slide is showing the title and the authors. Okay, let me switch. Bam. Okay, so this one is Omni titles. Omni titles, the user customizable display using an omnidirectional camera projector system. Authored by Jana Holland, Shio Miyafuji, Jefferson Pardman, Toshiki Sato, and Hideki Koike from Tokyo Institute of Technology. So are there the authors? Maybe not. I'm afraid no. Yeah. Until yesterday, they stayed here. But okay. Anyway, let's congrats to them. Okay. Okay. So next honorable mention goes to evaluating techniques to share hand gestures for remote collaboration using top-down projection in a virtual environment. Authored by Theophilus Teo, Kunihara Sakurada, Masaaki Fukuoka, and Maki Sugimoto. Okay, so please come, authors. Okay, very beautiful. Congratulations. They are also closer. Okay. Okay. Okay, finally, I'm very happy to announce the Best Paper Award. Okay, so the Best Paper Award is going to Manipulating the Scene of Embodiment in Virtual Reality, a study of the interactions between the sense of agency, self-location, and ownership, and authored by Martin Guy, Camille Junet Kelway, and Guillaume Moreau, and Jean-Marie Nomad. Congratulations. Okay. Okay, let's take a Okay, this is the end of the award ceremony. So I switch to the microphone to Jean-Marie.
Yeah, but this is the end of the closing session. Anyway, I think it just we just wanted to thank you all again for attending the conference. We hope you enjoyed it, and I wanted to say a big thank you to Maki as well, who spent a really long time trying to do everything for the conference and worked very hard for it. So let's thank Maki, and thank you all for coming here. It's okay. I think it's over. We can, unless you want to say something, Maki?
Okay, thank you very much for your participation to ICAT-EGVE 2022. And yeah, I think this is a conclusion of all about ICAT-EGVE. And still, we have APMA in the afternoon. So yeah, if you want to yeah, participate APMA, then please come back to this venue. Okay, thank you very much for your participation.